Good evening. So we now start lesson 10, around 1/3 of the way through the course. Congratulations. Now, so first a question from last time. For fx to be differentiable at c, do we require fx to be defined at c? I wasn't sure of the answer in that moment. I guess I was a bit tired because the answer is yes, it's right there in the definition. So the definition of the derivative f prime c is that it's the limit of this ratio. And to take this ratio, we have to have f defined at c. So the answer is yes, for f to be differentiable at c, we require it to be defined at c according to the definition of this course. And just to put that in a picture, so the picture of the definition is that you take just checking. Oh yeah, you can see me. I couldn't see myself for a moment. The picture of this definition is that you take a point P and you draw second lines from another point Q which approaches it. And to do that, you have to have the function defined at P. So the answer to that question is yes. Now, another question which was asked on the WeChat group, you see, so kindly provided this text a question. So question, is this true? Is the limit of a ratio of two polynomials otherwise known as a rational function, is the limit of this as x goes to 0 the same as the limit of all terms? Okay, so the answer is, let's see. So the general answer is this, that if I have the limit as x goes to 0 of some function of f and some function g of x, then the limit is the quotient of the limits if, do you remember the condition? Let me write it here. If this is not equal to 0. And both limits exist. So this is the quotient limit law, which we gave in lectures. Now, in this case, what is the limit of the top and the bottom? If I put fx is a to the n plus all those terms x to the n, and gx is b to the m plus all those terms up to x to the n. So I'm assuming here n and m are both positive. Otherwise, the sum in the question doesn't make sense to me. But then the limit as x goes to 0 of fx is just a to the power n. And why is that? Because the limit is the value of the function f0, and that's a to the power n. It's because f is continuous because f is polynomial. Now this symbol with 3 dots like this means because. You'll see it sometimes. And for the same reason, the limit as x goes to 0 of gx is b to the m. So the limit is equal to a to the n over b to the m if b is not 0, because that's the same thing as b to the m being 0. Okay, so I hope that fully answers that question. It's a good example of how to use the limit laws. Okay. Let's see the questions. Okay, so a bit of review. Because we've covered quite a lot quite quickly in the last few classes. But the slope of a graph y equals fx at a point x0 and fx0 is, well, we called it m, and it was given by a limit. And this limit was the same thing, if you look at the definition, as the derivative of f of x. And how to calculate it? Remember, it's the limit as h goes to 0 of this ratio, the slope of the second line. And as usual, we have to say if it exists. It may not exist. And then the tangent line is a line with slope slope m, which goes through a point. So that's y is fx0 plus f prime x0 times x minus x0. So for example, if I put y is fx and the function is 1 over x, and I want to find slope at a 1 over a for a not equal to 0. Well, how to do it? Okay, so we did this example before by calculating the limits directly. But now we have more rules for evaluating derivatives. So let's revise one of those, because I just remembered that I talked about negative powers. At the end of the last lecture, but maybe I didn't fully explain. So let's do that again. So the rule is, and then we'll come back to that example. For integers n less than 0, the rule is that the derivative of the nth power, like this, is n times x to the power n minus 1, and I need x to be non-zero for this to be defined. So note, so we did this right at the end of last time. So rule here looks same for a positive integer. So the derivative of the power x to the n is just given by reducing the power by 1 and multiplying by that n. So let's prove it. And this is a good reminder of some other derivative rules. So let m equals minus n. Now this is greater than 0. So we already know, we already proved that d by dx of x to the m, because this is positive, this is m times x to the power m minus 1. But we want to calculate d by dx for x to the n where n is negative. So this is d by dx of 1 over x to the m, because m is minus n. And then I can calculate this using the quotient rule for derivatives. So how does the quotient rule go? Remember, u over v prime, the derivative, is vu prime minus uv prime over v squared. So what does that give us? D by dx of x to the m. Oh no, I've written this wrong. So first I want to take whatever's on the bottom. So what's on the bottom is x to the m. And then I take the derivative of what's on the top, which is 1. So that's going to be 0. But let me continue. So then I take minus what's on the top times the derivative of what's on the bottom. And I divide by x to the power 2m. So this is looking more complicated than we wanted, but it's going to simplify nicely. So this is 0. It's the derivative of a constant function is 0. And because m is positive, we know how to calculate the top. That's m x to the power m minus 1 over x to the power 2m. Okay, and then that equals minus m times x to the power minus m minus 1. And that, because m is minus m, that's n times x to the power m minus 1, which is what we wanted to show. Okay, so that completes the proof of this derivative rule for a negative power. And now let's go back to this example, which was interrupted. Okay, and let's copy this equation of the tangent line, so we can use that. Okay, so for this integer, a minus 1, we can use this this law to get that f prime x is, well, the same thing. We reduce the power by 1 and we multiply by the original power. So that puts a minus in front of the x to the minus 2. Okay. So now the tangent line, I've just changed notation for this example. The tangent line is when x naught equals this a, And f prime a by the formula we just got is minus 1 over a squared. So this is the answer. Fa is 1 over a, and f prime a is minus 1 over a squared. So 1 over a squared x minus a. Okay, so for what did we do? We had a picture from before. I guess it was this. So for a equals 2, we again get this answer. Y is equal to half minus a quarter times x minus 2. Okay, and to simplify that, oh yeah, actually we should simplify up here first. So multiplying out the bracket, we get 2 over a minus x over a squared. So that's a beautiful formula. And at this level, we get 1 minus x over 4. And we can see that's the equation of the line I've drawn in the picture. Okay, hope that's clear. Any questions there? Okay, let's continue. So second derivatives. So we have the derivative which measures the slope of the graph. But we also have second derivatives which measure the slope of the graph of the slope of the graph. So let me write down what I mean. So f prime x is first derivative and we also have the second derivative by taking derivative again. With respect to x. So we'll give an example. So notations first. There's lots of different ways that people write this. So f prime prime x, the function of x, is the same as if y is fx. It's the same as this. So d squared y over dx squared. And why do we write the squares like that? Well, it's because this is d by dx, take the derivative of the derivative dy by dx. So you see it makes sense to have 2 dx is in the bottom and 2 d's on the top. And I can also write this remember that f prime x can also be written as y prime. Well, this can be written as y prime prime. So we say f prime prime, or we say f double prime. So other notations, which you'll see less often, but they're used in more advanced texts. So d squared applied to f, applied to x, that means the same function, or d squared with respect to x applied to f. That's also a function. So those mean the same thing. So we can continue also with f triple prime and 4 primes. In the end, we stop writing primes, of course, and we write f with a power, but in brackets, f to the n. And similarly, y prime 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 for the third derivative, and y to the power bracket n for the nth derivative. So let's do a simple example. This is not difficult, it's just adding more notation. So if I let y be x cubed minus 3x squared plus 2, then y prime is the usual rule for the derivative of power. We reduce the power by 1 and multiply by the original power to get 3x squared. And this one we're multiplying by 2 and reducing the power to x, and derivative of a constant function 2 is 0. And now y prime prime is given by just differentiating again. So x squared, I multiply by 2 to get 6 and reduce the power by 1. 6x is 6. And we can keep going. Y prime prime gives 6. And let's make some space. Finally, the fourth derivative of y is 0. So this is the fourth derivative. Okay, so now we know how to calculate lots of derivatives, and we have notation for doing that, and that'll be used through the rest of the course. So a section on the interpretation of derivatives, what they can be used for. And derivatives as rates of change. So definition and defining a word, the rate of change, and sometimes we say the instantaneous, spell that right, instantaneous, of a rate of change. Of a function f with respect to x at x0 is the derivative f prime x0 if it exists. So remark, remember once again that f prime x0 is the limit as h goes to 0 of this ratio, the change in f between x0 and x0 plus h, and the change in x, which is h. So that ratio is the average rate of change of f. From x equals x0 to x0 plus h. So when I take the limit, I can think of this as the instantaneous rate of change. So an example, so the area of a circle is pi over 4 times the diameter squared. Oh, okay. Yes. So I just noticed in my drawing program that if I make a drawing and then I hold down, the drawing program guesses what I'm trying to draw. So if I draw close to a circle and I hold down, then I get a circle. So with this, maybe my drawings will become better in the next few lectures. I think this is a new feature of the program. So what do I want? I want to draw the diameter here and the area A first. And question is, what is rate of change of A with respect to D when D equals 10 meters. I'm going to tidy this up, it doesn't really look like a D. So this is D. So the answer is the derivative at x0. So in the language of this question, it's dA by dd at d equals 10 meters. And that is pi over 4 times 2d get evaluated at d equals 10 meters. And so the answer is 5 times pi meters squared per meter. So meaning for every, let's just say for a 1 meter increase in D, we get a 5 pi meter squared increase in A. So you can have the relative rate of changes of any two quantities. So something like the price of a product, if that changes, how much does the rate of sale change? If you have a formula relating them, then you can calculate the rate of change. And also if something depends on time. So here's an example. The velocity of a body. And again, sometimes we'll say the instantaneous velocity. Of a body with position. There's quite a strange noise that I can hear. It sounds like maybe an animal. Yeah, so WRT is an abbreviation for with respect to. Okay, maybe the noise stopped. Oh. Continue the instantaneous velocity of a body with position. Oh, the noise is still going. S, a function of t at time t. So that is, it's itself a function of time, of course. It's given by the derivative ds by dt. So for example, if s equals t squared, so the position body is changing, but it's not changing at a constant rate. The velocity is changing, that's ds by dt, which is 2t. So as you can see from the graph, the velocity is increasing, and it's increasing linearly at time. So note velocity can be negative so if my graph looks like this, so a body that goes somewhere and then comes back, then yeah, so it's maybe snoring. Let me see if I can mute. I don't think I can because I'm not the host. So the TA in the room maybe mute. So we shouldn't be too tough on this snoring person. Okay. Yeah, it's as you say, it's relatable. Okay. So velocity can be negative if a body goes to a place and then comes back. The velocity is positive and then negative. It includes the speed, it includes the direction of the motion. But by definition, speed is always positive, and so we can write it as the absolute value of velocity. So in other words, it's the absolute value of ds by dt. So for example, if a car drives from A to B and then back, then the position of the car maybe has a graph like this, from time 0 to time 1 to time 2. And then what is the velocity, the ds by dt? Well, let's just draw a graph of it, because I think we can just read it from this graph. So the velocity, v, is 1 up to time 1, and then it's not defined. So the graph is not differentiable at time 1 sort this graph out in a minute. Yeah. But from time 1 to time 2, the velocity is -1. Okay, so v is ds by dt, which gives this graph. And note, v not defined at t equals 1. Okay, let's take a break. Okay, so I finished this example off with a graph of the speed. So that's as you'd expect. The speed is always 1, except at time equals 1, where it's not defined. Okay. So continuing. So how can we calculate acceleration? Well, the acceleration, let's call it a function of t, is the rate of change of the velocity and because the velocity is the rate of change of the position, this is the second derivative of position. And one more definition, the rate of change of acceleration is not a jerk j of t, dA by dt. So this is the third derivative of position, which I write d cubed s over dt cubed. Yeah. Okay, so let's give an example. Galileo's law for a falling body. Galileo's law. So imagine a body falling. I have a picture here somewhere. Going back. Oh, where is it? Here. Now let's move this to the next page. So if you drop an object and you wait for 1 second, then that object will go 5 meters. After 2 seconds, it will go 20 meters. After 3 seconds, it will go 45 meters. And the reason for this is the constant acceleration due to gravity. And that acceleration is g, is approximately 9.8 meters per second squared. Or in British units, feet per second squared. And the position, in terms of this g, is half g t squared. So, question. So how far does this fall in the time interval 0 to 2? So change in position is delta S. So half g is 2 squared, that's the position at time 2, minus half g, 0 squared. So that's half of 9.8 times 4, which is 19.6 meters, which matches the picture. So let me write, this is an interval of time. Okay, and now what are the velocity and acceleration at times 2? Well, the velocity is the derivative of s. So that's, well, let's write it out, half g times 2t, the derivative of t squared. So it's gt. And then the acceleration is the derivative of gt, which is just g. So as we said, it's a constant acceleration. And so the answer is, well, g times t is 9.8 meters per second squared times 2, so 19.6 meters per second. And this, as we know, is 9.8 meters per second squared. Okay, let's do another example. A slightly more complicated example. So a rock blown upward by an explosion at 160 feet per second. And so the height of this rock is, say, s, 160t minus 16t squared after t seconds. So let's calculate the velocity v. Well, derivative of t with respect to time is 1. Derivative of t squared is 2t. So here I get 32t. And the acceleration is minus 32. And this is, as usual, this is acceleration due to gravity. So let's take a look at the corresponding graph. Yeah. So we plotted the height S, that's the blue curve, and the velocity V, that's the yellow curve, on the same graph. And we can see, like we said, the rock is blown upwards at 160 feet per second. So the velocity starts at 160, but because of the acceleration due to gravity, the velocity goes down and becomes negative as the rock starts to come back down again. So let's calculate the maximum height. So maximum height happens when we have a horizontal tangent of ST, and that's if and only if S prime t is 0. So if t is a root of the derivative, that's if and only if ds by dt equals 0. That's just a different notation. And that's if and only if the velocity. So v is the upward velocity, and that's if and only if that is 0. So happens at t equals 5 seconds. Okay, but we want the height at that point. So the height, S, is, well, it's here, 160 times time 5 minus 16 times 5 squared. So that is 800 minus 25 times 16 is 400. So the answer is the rock goes up to 400 feet. So those are physical examples of rates of change. So maybe they're the easiest ones for us all to understand, but depending on your interests, see book for examples in economics, genetics, and so on. So these, of course, rates of change come up in all parts of science. We're now good at calculating rates of change for polynomials and some other functions. We're also going to need to study them for trigonometric functions. I mean, even to describe motion in the real world, trigonometric functions are very important. We'll see that. So what is the derivative of so first recall some identity we had, the double angle identity, for the sine of a sum of two angles. We said this was sine x cos h plus cos x sine h. And we can use that to calculate the derivative. So using this, our derivative is equal to, by definition, the limit as h goes to 0 of the change in sine over h, and I'm going to be able to rewrite that using my identity. Let me copy in a few more limits first. Just to make this easier to write. Okay, so first let's use this formula where we have sine x times cos h, but we also have a minus sine x. So let's go straight and write cos h minus 1. And then we have the rest of the identity cos x sine h like this. And we're still all dividing by h. Then so x in this limit is a constant. X is not changing in the limit, just h is changing in the limit. So I can take x out, and the question is, what is the limit of cos h minus 1 over h? And in the same way, I can take cos x out, and then the question is, what is the limit of sine h over h? And I'm also using the sum limit law. So using sum and constant multiple limit laws. And then, can I evaluate these limits? Well, sine h over h, we talked a lot about what the limit is there. The limit is 1, and cos h minus 1 over h, I can't remember if we calculated this exactly, but you can calculate it in the same way using the sandwich rule. Yeah, I'm pretty sure we did calculate that, and the answer is 0 for this one, and as we say, it's 1 for this one. And so the derivative is cos x. So the derivative of sine x is cos x. And in a similar way, we can prove that the derivative of cos x is, careful now, minus sine x. Okay. So an example of how these trigonometric functions appear in real-world problems. So imagine a spring pulled downward by 5 centimeters, and then its position S is given by 5 times cos t at time t. So I'll take a picture of this from the book, something like this. So the spring rests at position 0, and we start the motion by pulling it down to S equals 5, and then of course the spring pulls it back. It goes up to minus 5 and then comes back down again and oscillates like this according to the function cos t. So then, using our result above, I can calculate the velocity, which is ds by dt, and the derivative of cos t is minus sine t, so we get this. And I can calculate the acceleration, which is the rate of change of the derivative of the rate of change of the velocity. And because the derivative of sine t is cos t, I get that. So let's take a graph of these. So again, the position S and the velocity V are on the same graph. The position S is the blue graph. We start with S equals 5, and then S goes down to 0, down to minus 5, and then back up again. It oscillates. So the graph is the opposite of the picture with the spring, in the sense that when the graph is at the top, the spring is at the bottom, and vice versa. Okay, and what can we see from the graph of the velocity? Minus 5 sine t. Well, that's the pink graph, and that starts at 0 when we release the spring. And then the velocity becomes negative, and then it becomes less negative, and it becomes, you can see it becomes 0 at the point when S is minus 5, when the spring is at the top of its motion. So some notes on this. So the speed, which remember is the absolute value of V is the greatest when S equals 0. So let me draw in those points. So V is purple graph. So here S is -5. So the speed, I said wrong. Here V is -5. So the speed is 5. And here V is +5. So the speed is also 5. And here again. And you can see that these green points are where the blue graph passes through the axis when S is 0. So another thing we can note that the acceleration A is -S. So acceleration pulls spring back towards S equals 0. So when S is positive, the acceleration is negative. It's tending to pull the spring back towards the point S equals 0. The opposite. When S is negative, the acceleration is positive. So this is called, say, simple harmonic motion. Okay, so using the derivative of sine x and cos x, we can work out the derivatives of all the other trigonometric functions. So let me show you those. So the derivative of tan x is sec squared x. The derivative of sec x is sec x times tan x. And let me just give one example of how you calculate that. So just d by dx of tan x. Well, tan x is a quotient sine x over cos x. And we have the quotient rule for derivatives. We take the thing on the bottom, so remember it's u over v prime is vu prime minus uv prime over v squared. So cos x times cos x minus, let me move this out of the way. Okay. minus sine x times the derivative of cos x. And remember, the derivative of cos x has this minus sign in it. So then we have minus sine x. And we divide all this by cos squared x. So remember, cos squared x is just a way of writing cos x squared. Okay, and now this simplifies a lot because those two minuses cancel out. And so I get cos squared x plus sine squared x. And that's 1. Because of one of the identities we proved. And so we just get 1 over cos squared x. And that, by definition, is sec squared x. Okay, and note this derivative is not defined everywhere because tan x is not defined everywhere. For this, want tan x to be defined and that's equivalent to cos x being non-zero. So we need to divide by cos x in this calculation. And if you look at the graph of tan x in cos x, you'll see that it's true that tan x is defined when cos x is non-zero. Okay, so we can start in the last part with an important way to calculate further derivatives if I have a composition of functions. So remember, this means do function g and then do f. So what is the derivative of this function? So let's do a very simple example first. So if we take the function y is 3 over 2 x. So of course that's 1.5 times x, but it's also multiply x by 3 and then half. So in other words, composition of functions y is half u and u is 3x. So multiply x by 3 to get u and then half u to get y. That's the same thing. And of course we have derivatives dy by dx is 3 over 2. dy by du is half. And du by dx is 3. So notice that this derivative, let me make some space, this derivative dy by dx is dy by du times du by dx. And this also holds more generally. So note dy du and du dx are not fractions, they're just symbols. We said this before. That can think of them cancelling. So I mean, we have dy by du times du by dx. And we cancel the du's. And you can use that to help remember this formula. Okay, so what is the formula? And there's a picture here, here, yes. So in short, rates of change multiply. The derivative of the composition at x is the derivative of f at gx times the derivative of g at x. Okay, that's what this picture shows. So it takes a bit of practice to remember this. But let me write down the theorem. Chain rule. So if gx is differentiable, I'll just write diff at x and another function f of u is differentiable at u equals gx. So just like in the picture above, we've got x going to gx, and then another function acts on it. So we want that function f to be differentiable at u equals gx. Then the theorem says that the composition g then f, which is a function of x, is differentiable at x, and its derivative is the product of the derivative of f, that's f prime, at gx times the derivative of g at x. So this here just means multiplication. And we have two pieces to this formula. So first, the derivative of f at gx. That's the first part. And the derivative of g at x. That's the second part. And we multiply them together. So the formula I've written here is using functional notation. But we can also write this in the way we were writing it above. So if we write y is fu and u is gx, then what does this say? That, well, let me write the composition of these functions as well. So that y is given by the function g then f. So f circle g is g then f, and that's applied to x. So what does this say? It says that the derivative of the function g then x, sorry, the derivative of the function g then f on the left-hand side, and that's dy by dx, at x, now that's equal to the product of two things. So I'm going to do the red one first because it's easier. So the derivative of g at x, so that's du by dx at x. That's the easy one. The red one. And then the other one is the derivative of f at gx. So the derivative of f is dy by du at make a bit of space. Oh, I said this wrong. Dy by du at gx. So that's the blue bit. And as before, I multiply these together. Or, for short, I'll just write this formula. Dy by dx is dy by du times du by dx. And we'll start the next class with some examples of this. the use of this formula. Okay, thank you.